The second part of 3.6 has us doing the reverse of what we did in the first part. In the first part, you were given an equation, and we found zeros or roots by factoring. Here, I'll give you zeros or roots, and we'll work backwards to create the equation. A very useful component for this project is called the conjugate root theorem. A conjugate deals with complex numbers. If you have a zero or a root that's in the form a plus bi, and that's just a complex number. So if a plus bi is a root, then its conjugate, a minus bi, is a root too. Oops, that doesn't really quite look like the word I wanted it to look like. There we go. Then it's also a root. So the example on the right, pretty easy to kind of fill in the blank on this one. If 4 minus 3i is a root, which it just means the same as a 0, then the conjugate 4 plus 3i is also a root or a 0. Now you can have real solutions. For example, if x equals 3, then that means only one real solution for that. We don't have a conjugate for real solutions, just for complex solutions. Another useful tool in writing equations is called the sum and product rule. So sum is the answer when you add, product is the answer when you multiply. The sum and product rule will create a quadratic solution. So it either creates a quadratic polynomial or a factor. And the definition, make sure to write this out. It's going to be in the form x squared minus the sum will be the coefficient in front of x plus the product, and that will be the constant. So the sum and the product come from your two roots. Looking at the example on the right, we'll see this in progress. It says, what is the quadratic function, or what is a quadratic function with rational coefficients that has 6 and negative 13 as roots? What that means is x equals 6 and x equals negative 13. We have two zeros or roots for our polynomial, meaning it would be quadratic. To find their sum, it's really easy. You just add them together. 6 plus negative 13 equals negative 7. To find their product, we multiply. 6 times negative 13 is negative 78. Once you know those two answers, you can create your quadratic function. So in this case, p is our quadratic function. I'm going to write p of x equals. Remember, it's x squared minus the sum times x plus the product. I'm literally just going to plug in negative 7 and negative 78 into that equation. P of x equals x squared minus, the sum is negative 7, so I'm going to clean that up in just a second, plus the product, which is negative 78. To simplify this, notice we have a double negative for the 7. P of x would then equal x squared. This becomes plus 7x, and then minus 78. There's your quadratic function. Now we can use this to write higher ordered polynomials as well. In the next example, we'll keep it quadratic, but now we'll use a complex solution. It says, what is a quadratic function p with rational coefficients in standard form such that p of x has 2 plus 5i as a root? That means x equals 2 plus 5i. Based on the conjugate zeros theorem, we would also know that 2 minus 5i is a root as well. So I'm just going to put another root, using that conjugate zeros theorem. Since we have two roots, we can create a quadratic function. If we apply the sum and product rule, The sum is usually easier than the product. And what will happen when we're done is that all the i's will cancel out. We won't have an I in our quadratic answer. Take 2 plus 5i plus 2 minus 5i and add them all together. Well, the 2 and the 2 create 4, but the positive 5i and negative 5i cancel out. Therefore, the sum is 4. The product will require you to FOIL 2 plus 5i times 2 minus 5i. To get the product, if we do first, outside, inside, last, 2 times 2 is 4. 2 times negative 5i is negative 10i. But on the inside, 5i times 2 is positive 10i. And then positive 5i times negative 5i is negative 25i squared. In the middle, the 10i's cancel out because one's negative, one's positive. And then we have to recall what I squared equals. Remember, I squared equals negative 1. That means we're going to have 25 times negative 1, which is negative 25. And that double negative just makes a positive, giving you a product of positive 29. Once you know the sum and the product, we're ready for our function. P of x equals x squared minus the sum, which we said was 4, times x plus the product, which is 29. We don't have to simplify anything here, therefore P of x equals x squared minus 4x plus 29. That is a quadratic function that has 2 complex solutions. When asked to create polynomials that are higher ordered than quadratics, you want to make sure that all of your zeros are represented as factors, and then we do some foiling. So the first thing to do is determine all zeros. So we'll say real and complex. And that means to think about that zeros, or that complex conjugate theorem. From all your zeros, create your factors. Some factors will be just from real solutions, and some of our factors we can use the sum and product rule for. Last but not least, we get to FOIL all of our factors together. That'll be fun. And make sure when you're asked to write a polynomial function that you write P of x equals then your answer, or F of x equals, or y equals, whatever they want you to have. But you always want to generate an equation for your answer. All right, the last one that we're going to do in the video. Find a polynomial P of x with degree 3, and it has given zeros 2 and 3 plus I. So the first thing we're going to do is determine our zeros, real and complex. I know that it says the 0 is 2, that's 1 0, so I'm going to write x equals 2. And then I also have x equals 3 plus I. Since that one is complex, its conjugate is also going to be a 0. X will also equal 3 minus I. And that's all you do for step 1. Just make sure all your zeros are represented. Since we want a degree of 3, we need 3 zeros. And we have that, we're ready for step 2. To create your factors, anytime you have a real solution, like x equals 2, the factor is just what it would have been in the parenthesis prior to that. The factor then for x equals 2 is x minus 2 in parentheses. And we'll need that for step 3. So x minus 2. For the 3 plus I and the 3 minus I, we're going to do the sum and product rule. It'll eliminate the i's really quickly. And not if x. I wonder if... All right. Okay, so if x equals 3 plus I and 3 minus I, we'll find their sum by adding them together. 3 plus 3 is 6. The i's cancel, and that leaves the sum of 6. The product will have to FOIL. And you guys, make sure you take your time when you're foiling. Avoid careless errors in this part because we have a lot more foiling to do later. If we take 3 times 3, we get 9 minus 3i plus 3i minus I squared. The 3 i's in the middle cancel. 9 minus I squared, which is negative 1, becomes plus 1, which is 10. And now for this factor part, we're not going to write it as p of x equals. For the factor, I'm just going to put it in parentheses. X squared minus the sum plus the product. So x squared minus 6x plus 10. That's step 2, creating your factors. Step 3, I'm going to give myself a little bit of room here to make this happen, just to make sure I have enough space. Step 3 is to FOIL all of our factors together. We had our x minus 2. We also have x squared minus 6x plus 10. I'm going to take the first x in the x minus 2 and distribute it to x squared, and that would give us x cubed. X times negative 6 would be minus 6x squared, and x times 10 is positive 10x. Now I'm going to take negative 2 and do the same thing. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 6x is positive 12x. And last but not least, negative 2 times positive 10 is negative 20. Now in my final answer, I'm going to write p of x equals. And I'm simply going to combine like terms. I have x cubed, there's my first one. We have negative 6x squared minus 2x squared, that's negative 8x squared. We have 10x plus 12x, which is 22x, minus our constant of 20. So look at that, you guys. We've created a cubic function that has a real zero of 2 and 2 complex solutions. We'll finish the rest of our polynomials in class tomorrow.